Now we're going to talk about polar bonds and molecules, and I actually find polarity very interesting and all the things that come about with it. So let's first look at nonpolar covalent bonds. Now when we look at covalent bonds, we understand that the electrons are being shared. Nonpolar means that the bonding electrons are shared evenly. That means the electronegativity is equal. They both want the same electron, or both bonding partners want the electron the same, so they share it equally. This hydrogen has the same electronegativity as this hydrogen. They want it the same. This chlorine has the same electronegativity as this, so they want the electron the same. Okay, there's no real tug of war. They both want it the same amount. Nonpolar are equal partnerships. Let's say you're sharing a milkshake with someone, and they both have equal straws. They both share it the same. It's equal. They both want that milkshake the same amount. But it's when we get to things like polar covalent bonds, they still are sharing it, but one person has a much bigger straw. They have much more of it than the other. Or if you're sitting on a couch, you're sharing a couch with someone, this person has much more of the couch. They have more possession of it. And that is a polar, it's a pole. Okay, you have a pole here. Here are polar covalent bonds. This chlorine is much more electronegative than the hydrogen, so it pulls on that electron more. It wants it more. Like, let's say if you're sharing your cat, you have a pet cat, and you and your sister want to share it, but your sister has a real strong hold on it. She has more of it. She's holding higher possession of that cat. You have your arm around it. You're sharing it because your mom asked you to share it, so you are sharing it. But your sister has more of it. She has a higher possession. She wanted it more. You're like, yeah, I'd like to share the cat with you, but she wants it so much more. She's much more electronegative for the cat. She's holding on to more. You're just kind of putting your fingers out there a little bit. It's the same thing with chlorine here and the electron. The hydrogen they're still sharing it, but it's not equal. It's not equal sharing. Now this all has to do with electronegativity. So remember, these guys up here are the most electronegative. They want that electron the most. Na, fluorine, oxygen, nitrogen, or FON. Fluorine, oxygen, nitrogen, oxygen, fluorine. They are the highest electronegative. They're going to pull on that electron more than anything. Even if they're sharing, quote, sharing an electron, it's going to be uneven sharing. It's not going to be equal. A polar molecule means unequal sharing of the electron. They have two poles, a positive pole and a negative pole. Now these are not completely positive. They're just partially positive and partially negative. And we'll use the symbol delta, which means partial positive and partial negative. So when you see that, that means it's partial. You also will see this little arrow, which means my pen's not totally calibrated here. It's actually a new pen. I was very excited about it. I went into IT and they gave me a new pen. Very exciting. But notice here, this little arrow, that means the electron is pulled in this direction, and the way to remember it, there's a little plus here. So this plus sign, this little plus, that's the positive, partial positive, and this one is partial negative. Usually you will see just one of those symbols, either the arrow like this, or you will just see the partial negative, partial positive signs. So that means it's not an ion. It's not an ion, it's just partially. It's because this nitrogen is partially negative because it has most of that electron. It's holding on most of that electron. So these are polar, as opposed to nonpolar where they shared equally. And this is an interesting example here. While the fluorine is much more electronegative than the boron, because it's equally dispersed, there's partial negative here, here, and here, or the fluorines, and partial positive with a boron, they even themselves out. And the same here with carbon tetrachloride. Here, it's polar because the chlorine is getting most of those electrons from the carbon. Polar covalent bonds are where the electrons are shared unequally. Just because you have this bond, a covalent bond, where you're sharing electrons doesn't mean you're sharing it equally. I mean, really, are most things shared equally between anyone or anything? If you're sharing your popcorn at a movie with someone, you might take one little kernel every 2 minutes, but your friend might be just putting his mouth right in the tub and just chowing down. He's not even watching the movie. He's just chowing down on the popcorn. You're having one kernel every 5 minutes or so. So you're sharing it, but it's not equal. Again, the more electronegative atoms will pull on the electrons more than the less electronegative. Polarity and polar covalent bonds. So let's look at this in more detail. The more electronegative atom, the more it wants that electron, will attract electrons more strongly and gain a slightly negative charge. The less electronegative atom has a slightly positive charge. If we were to look at hydrogen fluoride, fluorine is much more electronegative. That means it wants that electron much more. So it will be slightly negative. The hydrogen will be slightly positive. So you can write it like this, and I kind of prefer it this way because you can really just see exactly, you can see the delta negative, delta positive. You can see which one is right off, which is negative and which one is, or partial negative, which one is partial positive. Here you can too. It's just, I think it's just easier showing the partial negative, partial positive sign. So the less electronegative atom has a slightly positive charge. They're still sharing though. It's still a shared covalent bond. We can say the same thing with hydrogen chloride. This is going to want it more. Or we can just draw it like this. We have partial negative and partial positive. Water, we have water here. Partial negative. Oxygen is more electronegative than hydrogen. So we have oxygen is going to be partial negative, hydrogen's partial positive. And you can even draw it too if you wish. There's a whole range of bonds. You have pure ionic where you're just absolutely giving an electron or two or more away. So you have a full charge, a full positive and full negative. That's ionic. This atom gave the electrons away, doesn't want anything to do with it. And the only reason they're together is because of the opposites attract with the positive and negative. Covalent, they're sharing, this would be a nonpolar covalent. They're sharing these electrons equally. A polar covalent, they're still sharing, but this guy has most of it. He's got most of the electrons. This one's just kind of hanging on. So if he's just hanging on to the electrons on the left, he's partial positive. On the right, partial negative, because the one on the right has much more of the electrons. And another visual, we have a water molecule. We have the hydrogens here and the oxygen here. So the oxygen is being more electronegative. It's grabbing that electron more. So we have the negative pole here and the positive pole here. It's just really greedy. That oxygen is saying, hey, I want more of that electron from both of you guys, from both hydrogens. And again, the electronegativity chart. Again, these guys are most electronegative. These guys down here are the least. It becomes important that we really know about the Fon elements because they have a lot of Fon. That's how we pronounce it out west. Fon. Not fun, but Fon. Hey, let's have some Fon with fluorine, oxygen, and nitrogen. They have a lot of Fon because they're so electronegative. Knowing that chart, I think it's kind of cool. But if we know the electronegativity differences between bond type, then we can see what type of bond they will have. So if the difference is between 0 to 0.3, it will be nonpolar covalent. They are sharing it equally. Example would be Cl bonded to Cl. That of course makes sense. They're going to have a 0 electronegativity value because they're both going to want that electron the most. They both have the same electronegativity. If you have a difference of 0.4 to 0.9, you have a polar covalent, but it's moderately polar. It's not so huge. If we have carbon and nitrogen, we see that carbon is 2.5, nitrogen is 3, so the difference there is 0.5. So this is the difference here is 0.5. Difference here is 0. So that's going to be moderately polar covalent. How about if we look at boron and oxygen? We have oxygen at 3.5, boron at 2. So the difference there is 1.5. 3.5 minus 2 is 1.5, so that's very polar covalent. And how about lithium and fluorine? Lithium is 1 and fluorine is 4. A difference between those, 4 minus 1 is 3. So anything greater than 2 is ionic. And that's a pretty strong. Anything with fluorine is, you're going to get a huge pull by fluorine. Oh, well, like, who cares? So what? You're partial positive, partial negative, la-ti-da. Well, the cool thing about that is you can now have not only attraction within molecules, but betwixt molecules. Okay? Meaning, if we have one molecule over here, we can have an attraction with another molecule over here. Okay, there's going to be an attraction here, this to this, because of the partial charges. And that's really the cool thing. And these partial charges are responsible for many awesome things in our life. These are intermolecular, between molecules, as opposed to intra. Now they are weaker than covalent, intramolecular, but they are still important. They're still very important. Not as strong as covalent, but still important. The attraction between polar molecules, intermolecular again. Now they are weaker than ionic or covalent molecules, but still important. Now the ones we're going to talk about are called van der Waals forces, named after Dutch chemist Johannes van der Waals. First one we'll talk about is dispersion. Dispersion, those are the weakest, and that's between polar molecules and also between nonpolar, which is pretty interesting. So polar molecules can be involved in dispersion, and also nonpolar molecules can also be involved within dispersion, with dispersion. Dipoles between polar molecules. So van der Waals force is very interesting. They're responsible for a lot of things. One thing they're responsible for is the stickiness on the bottom of a gecko's fingers. The gecko is it's pretty amazing what a gecko can do. They can climb all the glass and all sorts of smooth surfaces. That's because of the van der Waals forces on their fingers and the interactions between that and the surface they are walking on.